one forms on the Sierpinski.
Thank you. So this work is in work in progress. Is a joint work with Fabio Cipriani, Daniele Guido, and Jean-Luc Sauvageau. Okay, it's divided in three parts. In the first part, I will recall some of the results that Tepliaev has already mentioned, and then I will turn to the definition of one forms on the Sierpinski gasket, and then after that I will go to coverings of the Sierpinski gasket where one can have a potential for one form which is not exact. So the definition of the Sierpinski gasket is, has already appeared in Tepliaev's talk, is based on a iterative construction. We have three linear maps in R2, which are similitudes. They scale by the factor 1/2 and have as fixed points the three vertices of an equilateral triangle. Then this is the first step of the construction. You shrink the triangle in into three smaller pieces. And then you repeat the procedure. You start with this figure and you shrink that 3 times, and so on. And the end point, the limit point of this construction, the Hausdorff metric, is the so-called Sierpinski gasket. Some notation that I will be using. One scaled copy of the gasket here will be called a cell in the graph, in the fractal. Then there are 3 external edges, and scaled copies of these edges will be called edges of some level in the in the gasket. And then finally this is the largest hole in the gasket. There are infinitely many of them, and they are all obtained by scaling this larger hole with by using this a combination of similitudes. Okay, some topological properties of the gasket. It's a connected space, is locally connected and pathwise connected, also locally pathwise connected, but it's not semi-locally simply connected, which means that it has no universal cover. So this is to remind you of the Hausdorff measure that Tepliaev has already mentioned. This is the alpha dimensional Hausdorff measure. It's can be defined on a general metric space. You just need the notion of diameter. By using this Hausdorff measure, you can define what is called the Hausdorff dimension. Is the infimum of all these indices alpha, such that the measure of the set is 0, or which is the same, the supremum of all these indices alpha, such that the measure of the set is plus infinity. These two numbers are equal. For the gasket, this number is log 3 over log 2. The Hausdorff measure of the gasket with this dimension is non-trivial, is a finite number, non-zero. And the Hausdorff measure has a so-called set-similar property. It can be reconstructed by restricting the measure on the 3 cells, or on all the cells of a certain level, on a given level. Okay, there is also a different way. There are many ways of obtaining the gasket, but one that is often used is as the limit of a sequence of graphs, and you can see they are obtained by using the similitudes again. But by using these graphs, one can introduce the Dirichlet forms on the graphs, and then by suitably normalizing these Dirichlet or energy forms, we can obtain an increasing sequence, and the limit is what is called the Dirichlet form on the gasket. The set of finite energy functions is a subset of the continuous functions on the gasket. And once you have chosen a Borel regular probability measure on the gasket, you obtain an Hilbert space, and this couple of the energy form and its domain becomes a local regular Dirichlet form. So it has a generator, which I will denote by delta instead of minus delta, which is self-adjoint and positive and has compact resolvent. This is the relation between the energy form and its generator. But if you choose a Bernoulli measure, which is the restriction of the Hausdorff measure to the gasket, you can obtain the generator, the Laplace operator, also in a combinatorial, so more concrete way. Just consider the combinatorial Laplacian on a graph obtained by deleting the three external vertices. This one, and this one here, and so on. So this is the formula for the combinatorial Laplacian. And if you appropriately normalize this sequence of Laplacians, you obtain in the end a Laplace operator on the gasket, which has as domain a subset of the energy domain, of the domain of the energy, and it has this domain of the Laplacian has let's say a singular property. If f is a function in the domain, if its square is not in the domain of the Laplacian, it's not an algebra. I mean, there's no non-trivial algebra in the domain of the Laplacian. This property was proved by Tepliaev, if I don't remember, if I'm not wrong. Then one can define the outer normal derivative of a function on the three boundary vertices, and it's the definition is like the combinatorial Laplacian. And if you appropriately normalize it, you obtain in the end the definition of the outer normal derivative for a function on the gasket. And then by using all this stuff, you can prove an analog of the Gauss-Green formula of multivariable calculus, which says that the energy of F and G is this formula. It's like integration by parts. So there are some analogies between multivariable calculus and calculus on the gasket. One more analogy is so-called Weil asymptotic, which I remind you is was already mentioned this morning. The classical Weil asymptotic was obtained by Weil for a bounded open set in Rn. If you define the eigenvalue counting function, so the sum of all the eigenvalues less than or equal than a fixed number x, and counted with multiplicity, so the dimension of the eigenspace associated to the eigenfunction. Then for an open bounded connected set in Rn, this eigenvalue counting function goes to infinity like the n, like a power x to the n half, n over 2 power n is the dimension of the open set. And for the gasket, it was proved by Kigami and Lapidus that there exists a periodic function such that the eigenvalue counting function is proportional to this g of log of xr, or x over 2, times a power of x, ds over 2. So ds is something like this n here, and is what Tepliaev has called the spectral dimension or exponent, 2 times log 3 over log 5 or log 9 over log 5. So in a sense, it measures the dimension, the spectral, spectral dimension. Okay, there is also a notion of harmonic functions, and they are obtained as the solution of a minimum variational problem. We look for a function which minimizes the energy between all the function with finite energy and which have a given value at some set of vertices, the vertices of level m, let's say. And if you solve this problem, there is a unique solution, and this function is called M harmonic with boundary values, with given boundary values u. And for these harmonic functions, there is a weak maximum principle that says that the value of f is between the minimum on the boundary and the maximum on the boundary. So the minimum and the maximum value of the function is obtained on the boundary of a cell. This is a cell. Okay, the set of all harmonic functions is dense in the set of the continuous functions in K in the gasket. Okay, this is just a sample of all the results that have been proved on the gasket and on more general fractals. But there was missing the notion of one forms. The gasket is something like a one-dimensional object, so one can only talk about one forms. Anyway, we tried to we constructed a candidate for the set of all one forms by starting from a procedure which is used in non-commutative geometry, which is this one. It's called the set I will be defining is called the set of universal one forms associated to an algebra. So F could be in principle any associative unital algebra, but I will assume that F is the domain of the energy form. So you can define a differential, which is this map, goes from a function g in F to 1 tensor g minus g tensor 1 in F tensor F. F tensor F is the set of all functions on two variables. And then one can construct an F bimodule, which means a vector space which has two actions of the algebra F, one on the left and one on the right. The action on the left is this one, and the action on the right is more complicated, but it's related to the Leibniz rule for the differentials. And the set of all one forms is just a product of F and dg. dg is this one. So it's a formal definition. But anyway, one can do something with this formal definition. Here, by way of contrast, I recalled what one can define. What one can say is a combinatorial differential. One can obtain it. I mean, the object relates functions. let's say, continuous functions. Well, anyway, functions on the vertices, to functions on the edges. So the g is a function on the edges, and it's defined on each edge as the difference between the function on the terminal minus the function on the origin of the edge. So it's a different definition. But then on the set of all one forms, one can introduce a quadratic form which can be extended by bilinearity or sesquilinearity to be a semi-definite inner product, and also an integral, as always in the gasket, as a limit procedure on the approximating graphs. And one can prove that the above limits are well defined and finite, and moreover that if the integral is 0, then the semi-norm associated to this semi-definite inner product is 0. Vice versa is more complicated, but it's true. But then one can define, maybe if one is interested in integration of one forms, this definition can be natural. The set of all one forms divided out by an equivalence relation, which says that we consider as 0 a one form if the integral on all the length, on all the edges is 0. Okay, there are some special, or some especially interesting one forms on the gasket, which are of course the exact one forms, and there is a more general class of one forms which is also interesting, which is called n-exact, which we call n-exact, which is a generalization of exact one forms, and it's based on having locally a potential. An exact form is just a differential of a potential, and here we can generalize by saying inside any cell there is a potential, but globally there is no potential. And among these n-exact one forms, we found that there are, let's say that there is a special basis which is obtained by solving a minimization procedure. Well, n-exact means that that we have a potential for any cell of length n, of level n, but not globally. Yeah, exactly. Not necessarily the same. So I was saying that if we solve this minimization procedure, so the minimum of the semi-norm in the set of all one forms which are n+1 exact and have, let's say, integral 1 in the lacuna inside of this cell, there is just one solution for this minimization procedure, and is obtained by you know, if you assign the value at these 3 vertices of this smaller cell, you can obtain a unique solution of a minimization problem, which is called, let's say, harmonic function. So this d zeta sigma, which is the solution of this problem, is uniquely defined once you have assigned these values on this triangle and this value on this one, and so on. So there is the solution of this minimization problem is also obtained by computing the potential in this way, the function that has these 3 boundary values assigned, and the same here and here. Okay, the set of all these one forms is, as I said, an orthogonal system. It's not normalized. the seminorm is not 1. And the set of all these 1 forms is orthogonal to all the exact 1 forms. So the scalar product is 0 for with respect to any exact 1 form. So in classical situation, these forms should be called co-closed because they are orthogonal to exact forms. Since this gasket is 1-dimensional, there are no 2 forms, so any 1 form is automatically closed. So we thought it was sensible to call these forms harmonic because they are contemporarily at the same time, co-closed and closed. Okay, and then one can prove Hodge decomposition once one has the notion of a harmonic form. And the Hodge decomposition goes as follows. For any 1 form, one has a sequence of scalars so that one can construct what turns out to be a 1 form. And these k sigmas satisfy this relation, which is a technical one. This omega 0, even if it's an infinite series, turns out to be a 1 form with finite energy. And the difference between the starting 1 form and the 1 form we constructed by means of this d zeta sigma is exact. So omega is the sum of an exact form plus an harmonic form. And so this is the analogous of the Hodge decomposition. And as a corollary of this result, one can prove that the seminorm is 0 implies that omega is 0. Is equivalent to the 0 form. So the quotient, or what I called omega, inherits a pre-Hilbert space structure. So its completion is a Hilbert space. And then if one has a 1 form, in general, one would like to obtain a potential. And usually this is done by going to the universal cover. But since we don't have the notion, the universal cover of the gasket doesn't exist, we have to provide a substitute for that. And so this is the motivation for this construction. Let's introduce the triangle, which is the convex hull, the full triangle, which is the convex hull of the gasket, and then it's this should be T1. So you obtain you perform the same procedure that we played in the beginning, one of the ways of approximating the gasket. And then because the gasket embeds in this Tn, this is T1, and this is the generalization, you can pull the universal cover of Tn back to K and obtain a cover which we denote by Kn tilde. And because of the construction, because it's a pullback, the group of deck transformations of this cover Kn tilde with respect to K is the same as the group of deck transformations of Tn tilde, which is the fundamental group of Tn. And because Tn is just a bunch of circles, it's easy to compute. It's the free group with this number of generators. The number of all the symbols which have length less than n. Okay, if we collect all these Kn tilde together, we obtain a projective family, a tower of coverings. So we can take the projective limit, and this is this is denoted K tilde and is our substitute for the universal cover. It has some of the properties of the universal cover, One of them is the unique path lifting. Any path in K has a unique lifting to a path in K tilde up to the starting point. If you fix the starting point, it is unique. And it also has a pleasant property. The group of deck transformations of K tilde, which is the inverse limit, projective limit, sorry. Okay, it's the same. Projective limit of the group of deck transformations of Tn turns out to be the first check homotopy group of the gasket, which was recently proved, I mean last year, that this first check homotopy group contains the fundamental group of the gasket. So this K tilde is in some sense larger than the potential universal cover which doesn't exist. But we can do our construction. I mean, we would like to find potentials for the one forms. We can find potentials in a smaller covering, and this smaller covering is obtained by constructing a subcover of this Kn tilde. It's like an abelianized version. It is the subcover corresponding to this the normal subgroup of the commutators. And so the group of deck transformations of Ln tilde is just the abelianized of the group of deck transformations of Kn tilde, so it's the free abelian group with the same number of generators. So this is to show that Ln tilde is a subcover of Kn tilde. Also, the family of Ln tilde is a projective family, so we can take the projective limit, and the group of deck transformations is just a projective limit group. Also, L tilde has the unique path lifting property as K tilde had. Okay, so this is our result. If we consider n exact one forms, any of them has a unique potential which lives on L tilde, which lives in K tilde, but it has this technical property which ends up in showing that U lives in L tilde. And we can recover the integral of the one form omega as the difference between the potential at the starting point, at the final point, minus the potential at the starting point of any lifting of the edge E, and also the semi-norm of which is actually a norm. Now we can say that it is a norm. The square norm of omega is just the energy of the potential U, which is obtained in a similar way as was the potential as was the energy of the function on the gasket. And for the special n plus 1 exact one forms d zeta sigma, we denote by z sigma the potential. And these z sigma turn out to be useful because the projective limit topology on L tilde turns out to be the weak topology generated by these potentials z sigma. Okay, all the rest is technical. Yeah. Well, 15 minutes more or 10? Okay. Okay, so but now then we already we still have the problem of constructing a potential for a general one form, because I remind you that this theorem only works for n exact one forms, not for a general one form. And for doing that, we have to restrict once more the covering. Namely, we introduce a metric, let's say a pseudo metric to be precise, on L tilde, which is obtained by using the always these zeta sigmas, which play a very special role. And also we need one technical notion, which is the semi-norm n prime associated to, which is in a sense dual to the semi-norm n, which was introduced before. But anyway, we can define a pseudometric, which means a metric which can be also infinite on L tilde, and this pseudometric defines a topology on L tilde, which turns out to be finer than the projective limit topology. By using this this metric, we can define the length of any element of the group of deck transformations L tilde, and so we can say which of these deck transformations has finite length and which has not. The set of all finite length transformations turns out to be a subgroup which acts on any D component of L tilde, which means any subset of L tilde consisting of points which have finite mutual distance between one another. Or let's say the set of all points which have finite distance between from a fixed point, from a chosen point. Okay, so if you consider just a D component of L tilde, you can prove this final result, that any whatever one form, n exact or not, has a potential on any D component of L tilde, which is gamma affine, it doesn't matter. So if we recall the Hodge decomposition that we had already, so omega is the differential of a potential U1 plus some harmonic function, harmonic form, then this harmonic form has a potential in L tilde, which is just the series of all of the, let's say, an infinite linear combination of the potentials of these sigmas. So omega is a potential U. Omega is exact, is the differential of U, but U lives on a D component of L tilde. And finally, by using this potential U, the potential of the one form omega, one can prove this result, that namely that the integral of omega is just the difference of U computed at the end minus U computed at the beginning of the of any lifting of the path gamma. Okay, that's the end. Thank you.